Hello everyone, I'm Frank and welcome to Learn How to Sudoku, where we take a very easy, very Sudoku puzzle and we break it down in detail so that you can learn how to Sudoku. And actually in this puzzle, you'll learn a little bit about computers too, because we are going for our very easy puzzle is called Bitclock, which is a new constraint introduction puzzle by Jonesy. And this involves bit representations of digits, which is the underlying basis for all of computing. So everything that is represented, from letters to numbers to symbols to everything on a computer is represented in bits, which are zeros and ones. So we're essentially exploring that when we're looking at these puzzles. So I mean, I don't know. Maybe it'll help you like understand more about. I don't even know if that helps you learn more about computers. But if you think about it, everything is essentially represented that way. So if you take like an ASCII code, it's actually 256 different sets of representation, which can be from, I think the bottom 128 are set. And I think the next 128 are basically, if I remember correctly. So we have 128 symbols for ASCII. I think that's right. I don't think we use all 256. And then you have extensions of that, which are like called Unicode or whatever. But they all function very similarly. So the ASCII base is considered part of Unicode. And then the Unicode adds more ability because we have a lot more symbols we want to actually be able to represent. But yeah, essentially they all come down to zeros and ones though for a computer, because a computer can do those sort of things very fast, right? And they can basically flip things on and off very easily. And so that's how we represent things. Anyways, let's get to the rules. Hello. Hello, Jonesy. Thanks for taking a look at this puzzle. This is an introductory puzzle for a new constraint I'm calling Bitclocks. It's much simpler than it might first appear. Please take a moment to read the rule carefully, and the example will make everything clear. So, in the rules here, we have normal Sudoku rules apply, which means in every cell in the grid, place a single digit from 1 through 9 such that there are no repeats in any row, column, or designated 9-cell region. We have bit clocks, and I think we also have other stuff. Well, no, we don't. We just have fog of war. So we also have fog of war. I'm not sure if it's dynamic or if it's normal fog of war, or yeah, typical fog of war, I should say. Yeah, just go straight into Bitclock. So fog of war, you might be able to clear some cells in the fog. It just depends on the type of fog of war it is. I'm not sure which one it is going to be. Anyways, let's get to Bitclocks. Bitclocks. Each Bitclocks consists of an arrow cell, so they must be including this, and the 4 orthogonally adjacent cells around it, which means the cells that share an edge with that arrow cell. So for a bit clock, this is one bit clock here. This is another bit clock here. The digits in the arrow cells encode the parity, which is the odd and even of the 4 neighboring cells. Okay? Each digit 1 through 9 corresponds to a specific 4-bit parity code. See table below. And the arrow indicates the first neighbor, and the code is read clockwise around the 4 adjacent cells. For example, if an arrow cell contains a 3, which this does, The code, its code is odd, odd, even, even, because the odds are considered off and the evens are considered on. So that means in parity, in binary code, you would basically have the first digit is going, the rightmost digit is going to be the ones digit. The second rightmost digit is going to be the twos digit. The third rightmost digit is going to be the digit, fours bit. I keep saying digit, sorry, bit. And then the fourth rightmost cell is going to be the 8th bit. I'm going to take a cough drop right now because my sinuses are sort of acting up. So starting from the direction the arrow points and moving clockwise, the adjacent cells must be odd, odd, even, even. Read from left to right, right? So this is turned off, so that's 0 times 8. This is turned off, it's 0 times 4. This is turned on, so this is 1 times 2. And then this is turned on, so it's 1 times 1. And then obviously 1 times 2, which is 2, plus 1 is 3. That's why you have that representation, right? And every digit can be represented that way in binary, right? Yeah, and so that gets to the digit codes. 1 is obviously odd, 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 even, because the only bit that's turned on would be the last one, which is 1. 2 is odd, odd, even, odd, where the only digit turned on is the 2-bit, right? 3 again is odd, odd, even, even. 4 is odd, even, odd, odd, where the 4-bit is the only bit turned on. 5 is odd, even, which is the 4-bit and the 1-bit turned on. So it's basically, think of it as multiplication, right? You have 4 times 1 and 1 times 1, but you have 0 times 8 and 0 times 2. 6 is odd, even, odd. The 4-bit and the 2-bit are on. 7 is odd, even. 4, 2, and 1 bits are on. 8 is even, odd, odd, odd. Obviously, only the 8-bit is on. And 9 is even, odd, odd, even. And those are all the representations, and this is basically just binary representation of a base 10 number. Have fun. Okay, we will try. Additional insight, non-spoiler. Bit clocks can work in both directions. The arrow digit determines the parities of the 4 neighboring cells, but once you know the parity of some neighbors, they can restrict or even determine what the arrow digit can be, or which remaining neighbors must be odd or even to maintain a valid code. Yes. A useful mental model to think of the parities like binary switches. Odd equals off and even equals on. Yeah, I would prefer actually odds being on, because usually we represent that. But anyways, this is, people will do things the way that they do. I mean, probably they're using that because odds are easy. You have more leeway with odds as a setter. But typically when you have binary representation, 0 is considered off. And 0 is an even digit, obviously. So that's why evens being on is a little weird. Off, and if you represent something as on, it's usually represented as 1. You could have it as many different digits. So it could be an even digit too. But normally it's represented as a 1, which is obviously odd. So having it reversed is kind of strange, in my opinion. But, you know, it's easier probably to set. So that's probably why most people use off. Odd as off, because that gives you more leeway. Anyways, so in standard binary, 0100 is 4 because the 4-bit is on. Yeah, as I said, you have 1-bit, 2-bit, 4-bit, 8 bits. You have also 1632 in higher representations. But notice how 1 actually refers to even digits for all bits except the very first bit. Zeros and ones in binary are only characters to describe a state, on or off, and they are not the numbers themselves. Therefore, odd, even, odd, odd makes perfect sense. Yeah, I mean, that's fine. It just, yeah, it's for me, it's like as a former programmer, or I program still too, I guess. So, but basically, as a former software engineer, like basically, it throws me off a little bit to think of evens as always as being on. It's because kind of unintuitive for me. Anyways, those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's learn how to Sudoku. Okay. As I said, this is odd, odd, even, even. And again, evens are on. What digit is going to have even for the 8-bit and even for the 1-bit, right? 8, 4, 2, and 1. It can only be 9 because even is on, right? Even, odd, odd, even. So this must be odd, and this must be 9, which is an odd digit. So this is an odd digit. 3 is an odd digit. This digit must be even, and it has odd off here, that's fine. What about this digit? The ones digit is going to be on, so therefore this must be an odd digit. We have in the central box already 5 odd digits, so this must be even, and this must be even. These are then 1, 5, and 7. This has 3 odd digits. It must have, you can never have 4 odd digits in the clock, because that would be value of 0, right? Because 0 times 8 is 0, 0 times 4 is 0, 0 times 2 is 0, and 0 times 1 is 0. If you add it all up, it's 0. So you can't have that. So it has to be odd, 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 and this must be even. Well, what does that represent? Odd, 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 even, odd is 2. So this is 2. We have another even digit here, that's a bit clock. So this is even, odd, odd, something. Well, the only even digit then can be with the 8-bit on is 8. So this is 8, which means this is odd and off. This must be a 4-6 pair. Let's see, what else do we have? This is a digit, and it has blank, even, odd, even. Well, you can't have the 8-bit on because this is already adding up to 5. So 5 plus 8 would be 13. So this must be 5. And this must be off, which is odd. These can't be 5 anymore. They must be 1 or 7. 1 is odd, 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 even. 7 is odd, even, even, odd. Well, this 4th bit, which is the ones bit, is turned off. So this must be an even digit. Well, now this must become odd, even, 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 which makes this 7. So this is 7, this is 1. This is an even digit here. It can be 4, 6, or 8. This digit has an odd digit in the ones bit place. So it must be even itself. So this is even. Well, the only even digit that has an 8-bit on is 8. So this is 8, which forces this to be odd and odd here. Right? Those are off. So this is an even digit. This is 4 or 6. This is 4 or 6. That means, so these are both even digits. That means the fourth bit, the 1 bit, has to be off, which is odd. And this is already odd. The 4 bit must be on for both 4 and 6, so this must be even. This can't be 8. It could be, it has a 2 bit on, right? So therefore it cannot be 4. This is 2 or 6. Um, 5 has, this is 1, 7, or 9. 4, 6, 8. 2 or 6. The 8 bit is turned off. So this is odd. We don't know about this. 2 bits turned on. We have 1, 3, 5 in row 6. Oh, this has to be odd, even, odd, odd, which is 4. So this is 4, this is 6. That means this is odd, even, even, odd. This has the even digit turned on. So that means, sorry, the 8-bit turned on. So therefore, this is at least 8 or 9. Either way, if it's 8 or 9, the 4-bit and the 2-bit are off. So these are both odd. So since this is odd, cannot be 1 or 7, this has the even digit, has the 8-bit turned on with the even digit. So this must be 9, which would make this even and 8. So we have 9 and 8 here. This is even, odd, odd, even. So these are odd. This is even, odd, odd, odd. So it cannot be 8. This is 4 or 6. In this lower central box, we have 5 odds, so this must be even here. This is an odd digit, which has the 4-bit and the 2-bit on, so it must have the 1-bit on too, and this is 7. Does not have the 8-bit on, obviously, so therefore that's why that's 7. This has the 8-bit on, and cannot be 9, so this must be 8. Which leaves these as odd, because it's even, odd, odd, odd. We have 5 odds in row 6, which eliminates odds in the rest of the row. Sorry, column. 5 odds in column 6, which eliminates odds in the rest of the column. So this is even. This must be 2 or 6. This must be 2 or 6. This digit has an odd digit at the, on the 1's bit, which means it's off. So this must be an even digit. Cannot be 8. Could be 2, 4, or 6. Cannot be 2. So this is 4 or 6, which necessarily has an even digit on in the 4's bit. Well, we have 4 even cells, even digits in this upper central box, which leaves odd digits in the remaining boxes. So this becomes odd, even, odd, odd. So this is 4, which makes this 6. That makes this 2. That makes this 4. This is 2, and this is 6. Okay, so this is a dynamic fog of war. This is an odd digit. You have the 4-bit and the 1-bit on, so this can never be 9. So this can never be on. it's off, so that's odd. Which means this is odd, even, which is 5. So we have 5 there. Remaining digits in column 4 are 1 and 3. This is 2 and 8 here. Where's 5 in column 6? It has to be here, because it can't be there. So this is 3 now, which eliminates 3 here, so it's 1, which eliminates 1 here. This is 3. That leaves that as 1. This can't be 1 here. 1 is odd. Okay. This is an odd digit, so therefore the 1 bit must be turned on and is even. So we have even here. This cannot be 9 anymore. It can't be 7. It has to be 3 to be odd, even. Because that's the only even at the end without the 4-bit on and without 5. So this is 3. Therefore, this is odd. We have odd and even. So this must be at least 4. The 4 bits turned on, so this is 5, 6, or 7. This has neither the 4 or the 2-bit on. Cannot be 8 because of 8 in the column. Can't be 1 because of 1 in the box. So this has to be 9. So this is 9, which means this is on, which is even, and this is on as even. This is an odd digit. We have 5 odds in column 7. So this can't be odd. This is even. This is an even digit. So this must be off in the 1's bit, which is odd. Could be 8. This is 6 or 8. It cannot be 6 because 6 would have to have the 4 and the 2-digit on, and 4 is not on, so this must be 8. So this is 8, which forces this to be on and is even. This is off and is odd. We have 5 odds in the upper right-hand corner, so this is even. 6 cannot be either of these, so this is 6 here. That leaves 2, 4 remaining in the rest of that box. This can't be 2, this can't be 4 or 8. This is 2, 6 is a pair, which eliminates 2 and 6 in the rest of the column. So this can't be 2, this is 4, this is 2. Okay. This has even as the 1 bit, which means it's on, so this is an odd digit. Can't be 7 because that would require even. So this must be 5 or 9. This has an odd digit in the 1's bit, so that's off, which means that's even. Cannot be 2 or 6. It's 4, 8, but it doesn't have the 8-bit turned on, so it must be 4. So this is 4, which means this is turned on, this is off. We have off. This is at least the 4-bit on. Cannot be 7, it's 5 or 6. Remaining digits of row 2. Excuse me. We have 1, 5, 6, 7. This can't be 1 or 6. It's 5 or 7. This can't be 6. It's 1, 5, or 7. This is 5, 7, 9. This is 7 and 9. Oh, we have 5 odd digits in row 3. This 9 eliminates 9 here, so this must be 7. This is 9. That leaves this as a 7 here. 7 eliminates 7 here. So this is 5. This is 3. 5 eliminates 5 in the rest of the row. These are both even. And this must be a 1, 6, 7 triplet. If it's 6 or 7, this is guaranteed to be even. Right? Because you have to have a 4-bit on and the 2-bit on for both 6 and 7. Since this is even, the only even digit is 6. So this is 6, this is 7, this is 1, this is an odd digit, and this must be turned on. We have 4 evens in the upper left-hand box. That leaves the remaining digits as odd. We have 5 odd digits in column 3. That leaves the remaining digit as even. This is a 2-4 pair. This is 8, and we have a 5-9 pair in the odd digits in the rest of row 1. So this is 8. One cannot be here because of 1 in the column. This 3 eliminates 3 here, so this is 5. Which means this can't be 5. This is 9. This can't be 9. That's 5. This can't be 5 or 9. It's 7. 5 eliminates 5 here. This must be 2, 6, or 8 here. It cannot be 8 here. Where is the 6 in column 3? It must be one of these 2 digits, which means this can't be 6. So this is 5 and is red. So that means it's odd, even, even. What are the remaining digits in column 7? 1, 3, and 5. This can't be 5 because of 5 in the row. This can't be 5 because of 5 in the row. That's 1, 3, which forces this to be 5 here. Okay. This is even. Cannot be 4, cannot be 8, so this is 2 or 6. We have a 2, 6, 2, 6 pair in... Oh, we have 4 evens in this lower left-hand box. That leaves the remaining digits as odd. And we have a 2, 6 pair in that box, too, so that eliminates 2 and 6 in the rest of the box. So this is 8, which makes this 2, which makes that 6, which makes this 2, which means this can't be 2. That's 4, which makes that 2. Okay, remaining digits in row 8 are 1, 3, and 4. This can't be 1. This can't be 3. Both 1 and 3 and both 1 and 4 have the 8-bit turned off, which is odd. So this has to be 3. This is 1, and this must be 4. And is the even digit. So the 4-bit must be turned on, and the 1-bit must be turned off. This 3 here eliminates 3 here, so this is 1. We have 4 even digits in column 8, so the last digit is odd. This is 2. So 2, which makes this 6, which makes this 2. 1 eliminates 1 here, so this is 3. We have 5 odd digits in row 7, so this must be even. That makes this an odd digit here. Remaining digits in row 5. We have 4, 5, 6, and 9. Well, this can't be 5. Can't be... So 9 would have to have an even digit as the 8-bit, which is not allowed, because that's odd. So this is 4, 6, which means the 4-bit is always turned on, and 4 and 6 are both even. So these are even, therefore that makes this odd. The 8 is remaining as the even digit in column 1, but it cannot be here, it cannot be here, therefore the 8 has to be here. And we have 4 even digits in the left central box, which eliminates even digits in the rest of the box. So these are odd. This representation is 8, 4. The 4-bit is the only one that's on. So this must be 4. We have 5 odd digits in row 5, so that makes this even. We have 4 even digits in row 4, so that makes this odd. We have 5 odd digits in row 6, which makes this even. So this must be a 6. We have 5 and 9 remaining in row 5, but this can't be 5 because of 5 in the box, so this is 9, this is 5. And that representation works. Off, even, off, on, off, on. This is 6 here, which makes this 4 and this 8. So now the rest is just doing Sudoku. 1 can't be here in row 7, so where's the 1 in row 4? I don't know why I said 7. This is 1. This has to be 7 and 9 remaining in row 4. This has to be 3 remaining in row 6. We have 1 and 7 remaining in column 1, and this can't be 1 because of 1 in the row, so this is 1 here, this is 7. We have 3 and 9 remaining in column 2. This can't be 3 because of 3 in the row, so this is 9, that's 3. That leaves this as a 9, this as a 7, which makes this 9 and this 7. Thanks for playing. Greetings, Jonesy Killer Joe on LMD. Okay. Yep, so that's an introduction into bit clocks. As I said, for me, it's a little unintuitive because odd is actually off in these scenarios. So I always have to think through what does odd and even mean. But maybe for you, I mean, I've actually seen other ones. Other people have done bit arrows, and that was with the correct or whatever. The way that I'm used to having the on and off set, where even is off and odd is on. But yeah, I don't know. You can do it either way if you're setting. It's fine. Anyways, I hope you enjoyed this episode of Learn How to Sudoku, and I'll see you next time on Frank Puzzles. Take care.